Try to compute V1 of 3 on that problem. Okay, so I'll give you a couple more minutes, and then if you're done with V1 of 3, then start thinking about what's V1 of 1, what's V2 of 1, what's Vk, and when does Vk of 1 actually change from V0 of 1. Okay. And you start thinking about it, you start understanding what happens in MDPs. Yes?
So you need to incur a penalty for hitting the wall and staying in the same state?
We talked about the whole thing, right? I mean, basically it's the same model. I'm not making the problem different. The usual idea is if you hit the wall, you stay back in the same state, at which point you will get the reward. Okay, so in general, actually normally in MDP, every time you get to the state, you get a reward. So simple MDP problem, you can just keep going to the candy state and keep on repeating going to that candy state, and you will get infinite amount of candy. You know, basically lots of reward. So that's just what we looked at. By the way, so those of you who had started doing the homework part 2, I know at least somebody came to my office and asked some questions. Actually, there was a finite horizon MDP problem there, and so you should be knowing how to do it. Yes?
So you do have to take the exit action, right?
What exit action?
You have to take the exit action to get back to
No, there are only 4 different actions everywhere. Go up, go down, go left, go right.
So if I'm in 3-3, I'm saying when you move once, that's not enough.
I don't understand what you're saying. No, again, all you are going to do, you're computing V1 of 3. That means if you have one step to live, what's the value of 3? And it should be understood. Basically, this is what we discussed for the last class. Yes. And you're not trying to, again, this is something that your computer has to do. So it doesn't understand how images look. It's not doing image recognition. It's not doesn't have common sense. It's just a simple math calculation. It's just a bit of arithmetic. And that's all I'm asking you to do. Okay. Anyone has a handle on this? Who has a handle on this? Otherwise, we should just cancel the class and ask you to check the last class again. Has anybody actually had a sense of how to compute V1 of 3? 3 is the state, yes.
So you do like, if you're going to head towards the final state, you do 0.8 times 1 plus the reward that you're currently in. So 0.8 for 3 plus minus 0.04.
Okay.
That'd be,
But why do you think you will be heading towards the current state?
because you're going to work your way back from the reward. The
No.
final terminal
So
state.
here is so you got, I think, you have a second order problem. The rest of these guys have first order problem. They don't even know how to start. You started, but you have a second order problem. You don't, during the value iteration, you don't decide what action is going to be taken at each state.
Yeah.
You actually consider all actions and see which one winds up giving the highest backed up value. And then, now because this problem is extremely simple, it's crying out saying obviously the best action would be the one that goes, to the right.
Otherwise, you do like 0.1 times the value of those squares. And that
So
sums
basically
up.
you have to compute, okay. Basically this is what you have to do, okay. So first of all you realize that V0 is given because, to compute V1 you need V0, right? And we know V0 because V0 is nothing but R of the states, rewards. Rewards of the states are known because that's +1, that's -1, everywhere else it's minus 0.04. We have said this. This is what we kept repeating last time. Okay. And then so V0 of xy is nothing but R of xy. The xy happens to be the state notation here. Normally we used to talk of R of s and T of s. The state itself is the coordinates of the state right now. Okay. So now to compute V1 of 3, basically you have to do the Bellman update. Okay. And what does the Bellman update say? If you are going to be in 0 point, because you are in 3, 3, you have to be, actually this is, it's not max here. Okay, so this max is not the max here, so you should actually put a max here. Okay, so you are going to be, you're trying to compute the value of 3, 3 with one action to take. So since you will be at 3, 3, you will get whatever is the immediate reward of 3, 3, which is minus 0.04. Plus, the action you're going to take is whatever is the best action. Okay, to do that you have to compute the value of each of the actions, the back-propagated value of each of the actions. Okay, so now what are the 4 actions? You have going right action, going left action, going up action, going down action. Okay, so for each of them you have to compute this expression. What is this expression? This expression is saying if you are doing left, then if you are in 3, 3, if you do left, you then get to this state, or try to go up that way, which means you remain in this state, or you try to go down this way, that means you get to this state. Agreed? That's what the model is. Okay? So for each of them, there are probabilities of those happening. So the probability of the transition that you go from 3, 3, when you do go right, from 3, 3, you will get to 4, 4. That probability is how much? That's 0.8. Because we said that when you, in this particular setup, we assumed that the direction you are trying to travel, you will actually travel in the direction with 80% probability. And you will travel in the orthogonal directions with 10% probability each. Right? Yes?
So the probability model is pointing towards the actual goal, it's not actually up. So right here, it's at
What?
23.
So this action is going right.
Okay.
And this action is going left. This is up and this is down.
Oh, okay, got it.
All this is saying is basically how the action model is written. Again, I'm worried about these kinds of questions. Please do ask the questions because that will be way, I have a sense of where people are and whether you came to watch the performance or to understand the class. That is something that I always worry about. So basically, this is just to show that if you're trying to go in this direction, whatever that direction is, you go in that direction with 0.8 probability and the other 2 directions with 0.1 probability. If you did understand this, a lot of what happened last class should have been sort of gobbledygook, essentially. And again, thank you for asking the question, because the only questions that are not, the only stupid questions are the ones that you're basically not asking yourselves, because then you will pay for it later on. Okay, so this is 0.8 times plus 1 plus 0.1 times you try to go up and you stay in the same states, so that's minus 0.04. And then similarly 0.1 times minus 0.04. Right? Now this, by the way, it's a calculatable number. You can see that, right? This is a bunch of multiplications and additions. And then you add that to this, it will give you the actual value. So can somebody tell me what the value is? Calculate it.
0.752.
What? 0.7? 0.759. So what? 0.752. So apparently this here will come to 0.752. I don't know why my camera so it should be 0.752 on that one. I have to write this and some question for that. Okay, just remember that. And then you will have to compute all the other 4 expressions. If you are a computer, I mean, since you guys know that all these other expressions would be computed, and then you will take max over all these 4 expressions. And you can see, just because you understand the semantics of the problem, that it's going to be, this will win. So what will come out of the max of all these 4 would be 0.752. Okay? Okay. The other ones would be smaller, but in general problems, you have to actually compute each of these expressions and take the max. You don't know. Your computer doesn't know what you know in this case. Do you understand what I'm saying? Okay, so basically, V1 of 33, V0 of 33 was how much? V0 of 33 is how much? Minus 0.04. What is V1 of 33? We just told you. V1 of 33 is 0.752. Okay? So has the value of this guy changed from V0 to V1? Yes. And is the value connected in any sense to its reward? No. Immediate reward was minus 0.04. But then actually you are realizing that if you have just one step to live, it's a pretty nice state to be living in. Because you are connected to a rich person and you can get to that rich person, that rich state. Do you see what I'm saying? Okay, now that you realize this, I was hoping that people are understanding that all of this was in notations of this kind last time. And those notations essentially correspond to numbers according to the models. And if you don't see it, then it's all gobbledygook to you. Okay, MDP is very simple. It's actually an extremely easy to write program, right? And that's what you're doing in the homework. Was there a question? Okay, the other thing that I was asking is, now that you realized that V1 of T3 went all the way from minus 0.04 to plus 0.752, which is a huge change. And it also shows you that value has nothing to do with reward. Value has nothing to do with reward. Okay, let me ask you a couple more questions, assuming that this is actually going in. One other question I want to ask is, will values ever go down? But that is the second question. First ask this question. What is V dash of 1, 1? V1 of 1, 1. What's V1 of 1, 1? No, so wait. So V0 of 1, 1 is how much? Negative 0.04. What is V1 of 1, 1? So basically you will, because you are in V1, 1, 1, you will get the minus 0.04, right? And then I'm asking you to actually do qualitative reasoning, okay? Basically, all the other guys are still, V0s are, V1 is computed in terms of V0s, right? V1 is computed in terms of V0s. So whatever you do, it will be, whether you go up, whether you go left, go right, or go left, any of them, all of them will be equal, first of all. You can realize that, right? Because all states have minus 0.04 as their V0 value. So max of all of them would be any one of their values. And so let's just compute that value. It would be 0.8 times minus 0.04 plus 0.1 times minus 0.04 plus 0.1 times minus 0.04. Which would be, this whole thing would be minus 0.04. Okay, so this minus 0.04 is added to this minus 0.04. So you would get what? We got negative 0.08. So that leads me to the next question. As the value iteration is going on from V0 to V1 to V2 to etc., if you sit in one state and keep looking at the value of it changing, does it monotonically increase? Does it monotonically reduce? Or you can't say either. I gave you an example already, right? Because I showed you one case where it went from minus 0.04 to 0.752. In another case, it went from minus 0.04 to minus 0.08. So it can increase as well as reduce. So really what happens? So then the next question would be, so what is V11? That will be 0.08, minus 0.08. What would be V211? Negative 0.12. Okay? The question is, will Vk ever be, actually in fact this is not the right question to ask, will Vk ever become positive? Will Vk ever be positive? Do you see what I'm saying? Will Vk ever be positive? For Vk of 1, ever be positive?
When you get to the reward, it's positive.
What?
When you get to the reward.
No, so how does that happen? So you have to think of what is happening in the values, right? In the beginning, so all of them had V0 values, which was just the reward. Then the V1 values came in. When the V1 values came in, this guy became more positive than before. This guy actually becomes quite a bit negative than before probably. All these other guys became somewhat more negative than before. Do you see what I'm saying? Okay, now the question is, will they ever become positive?
Yes.
It will. Now, when will that happen? Why 5? Because by seconds, so the way to think about this is this analogy. You have a rich uncle somewhere, and if you just find your way to them, you can ask them for money. As long as, and you're trying to figure out whether you have a rich uncle by looking around your neighbors. If they're richer than you, you will say, can you give me money? Right? If you have an action of finding a way of getting them to give you money, you will become somewhat richer. Okay, what was happening to this poor guy in the beginning, what was happening to this guy is, he started, this cell started thinking, I'm just by myself, I don't even have time to ask anybody. So I'll just have my immediate reward. But then when I have one step to go, then I realize, well, I have some neighbors. The neighbors are the cells that the actions can take me to. The cells that actions can take me to. When I say neighbor, those are the ones that you are able to actually reach using an action. Okay? And it realizes by using its 4 actions that one of those actions is actually taking it to a very rich cell with a pretty good probability. Because of which it suddenly realizes, I'm not as much of a loser as I thought I was. I have some rich people that I know, and I have some non-trivial probability of getting them to give me some of their value. You see what I'm saying? At that same time, this guy looks around and finds that he was mostly, as of now, currently surrounded by losers just like him or her. And so they will only give this guy their negative valuations. Because they too think, because this guy at the V1 time, V1 time, this guy is dependent on the V0 of these cells, right? Those are the only cells it can reach. And their values will still be the reward values. Now if you take the V2 time, that means 2 steps to go, it'll be interesting to realize that these guys will still be negative. Because the message of there being a rich uncle is slowly propagating through the cells. You understand what I'm saying? So you will become rich too when you realize that there is a way for you to reach the rich guy. Or you will become extremely poor if you realize that there is no way you can stop from being, basically robbed by one of your neighbors, one of your transitive neighbors. That's what is happening in value iteration. Okay? So if you were to consider drawing what happens to the, what happens, let's say, to the value of each of these nodes, and let's say the true value, no, this is the value, okay, true value as in, let's say, for V10,000 S. I'll just say V10,000 S, actually in a minute I'll talk about V infinity S soon enough, okay? If let's say at that time, finally the value is something like that, that's where the value is. And the immediate reward that you are starting with is obviously sort of negative, in this case. The question is, as you go in the finite horizon MDT iterations, 1, 2, 3, etc., the idea is eventually you will reach the V10,000. But the way you reach is not necessarily monotonic. In fact, in this case, in the beginning, the guys who are negative become more negative, and then will slowly start raising. Do you see what I'm saying? And in fact, so basically, that's the point that you want to understand, that in value iteration is a sort of a message passing about your neighborhood. Okay? Do you see what I'm saying? It's basically a message passing over your neighborhood, and if your neighborhood does have high value bearing states, and you have a way of reaching them through your actions. First of all, the neighbor means you have a way of reaching them. Okay? So if one of your neighbors is high value bearing, then you also are sort of high value bearing. If one of your neighbors are really, really low value bearing, and if you can't avoid them, then you too are low value bearing. Now notice the distinction I made. When you have a high value bearing node, you will certainly be high value bearing. But just because you have a low value bearing neighbor doesn't mean you will have to be low value bearing. Do people understand why? Because you're doing max. Okay? So you don't have to, just because you have a loser friend doesn't necessarily mean that you too should be a loser. You're only doomed if all your friends are losers. Okay? And whereas if you have one winning friend and you still are a loser, that's because you don't know how to plan. Do you understand what I'm saying? Because you have a winning neighbor, and that means you actually can do an action to reach that winning neighbor, whereby you can kind of take some of their value for you. And if you're not doing it, you have only yourself to blame. Okay? So that little equation that we have has all these nice, behaviors that are just built in directly. I didn't do anything new. I'm just following that equation that I wrote about value iteration. And also remember this, in fact, in the textbook, I forgot to get the picture. In the textbook, they show, for the infinite horizon case, they show the values of the states as the number of iterations progress. Okay, and then notice that in the beginning, actually as the iterations progress, your value estimate is farther away from the true value. But then slowly it starts catching up and becomes closer to the true value. Okay, and again, the other thing that's happening is everybody around you is updating their losingness, winningness based on their neighbors and the messages passing to them. And you are at the same time updating your value based on your neighbor's value. But if you do this long enough, essentially, you will, the fact that you're connected to some rich neighbors will come back, will propagate to you. Okay? And the next part that I was talking about would be about infinite horizon MVPs, where in essence, I'm talking about V infinity S. That means if I just keep doing infinite number of iterations, then what would be the value I would get? And the ideas would be the same almost, except for the discount factor that we started talking about at the end of first class. Yes?
So I want to ask one thing. It's like we are evaluating that an action by which we cannot return to the state in which we are, and that is the maximum. That is out of that action is the maximum out of all the possible actions. So how can we?
I'm sorry, I didn't catch the question exactly.
Like I'm in a state, I'm evaluating all the actions, and the maximum of all that like value which is coming from that action, that action guarantees that you will not reach that state back. Are you getting my point? Like if I'm
Yeah, how
at
does
3,
it matter? Okay, fine. I mean, it doesn't make any difference whether that action gets you back to that state with.
so how can I like take that value for the next like if that action at V133 is getting me a value with
So is your point something related to the fact that when I was in this state,
Yeah.
when I tried to go up, I came back to V33?
what I'm trying to say is that by going to right, we are having a maximum. We will try to do that, right?
No, again, please don't put, what is that? Don't put the cart before the horse. Okay, you don't decide what action to do and then do Bellman update. You do Bellman update and figure out what action to do.
Yeah.
Okay, first of all, do people all understand? You know, when somebody came to my class, my office hours and say, as I'm going to do this action, tell me how to do Bellman update. If you know what action to do, you don't need to do Bellman update. You know the policy. Bellman update is the way you figure out what action to do. Okay, now,
So if we are doing an Bellman update, we are assuming that this action will be taken, right? Like
some action will be taken.
that some action will be taken.
Whatever is the max,
Yeah.
whatever comes out as the max of
Yeah.
these will be taken.
So that max action guarantees that you will not return to this state because the probability of remaining that state is 0.
Okay, that is, you're just saying in that particular problem that is the case.
Yeah.
Okay, so
So
what
how
happened?
can I get the next, like if that was the VK value of that state, how can get the VK plus 1 value of that state?
Now, how
Because
does it matter?
how can I use that reward point?
I'm sorry. No, so in this particular case, think about this. So if I were to take this, okay, and if I were to change the problem such that when you try to go right,
Yeah.
you either go right or you go down.
Yeah.
That's it.
Yeah.
Then basically you will never stay in this state.
Yeah.
What's wrong with this? That will
So-
still give me a number that would
Yeah.
be the value of 33.
So but
V1
that,
of 33.
how will I calculate the value of VK plus 1 if that is the
That's
case?
right,
then?
V2 would be in terms of V1.
But we are
Okay,
assuming.
I'm sorry. Let's take it offline. You know, I think you were confused at some level, and I'm not really sure that other people have that same confusion. So all I can say in your case is there is nothing that's actually going to have given you trouble. Okay, so basically you will be able to compute V1 of 33, because of which you can also, once you can compute V1 of everybody, you can also compute V2 of everybody. And once you can compute V2 of everybody, you can compute V3 of everybody. Okay, there is no inconsistency that you would get into. If you want, you know, we can talk later. Other questions? Yes.
I was just curious about the terminal node, because it doesn't seem like this Bellman update takes into account the fact it's a terminal. Like if you have 20 rooms, but ideally you're moving for the terminal state, and you still have like another 15 rooms left, is the value of the terminal
In the
node-
finite horizon case, so basically, again, I think you only consider the number of moves that you have left. Okay, so what you have to understand, I think you're worried about the fact that why did I prematurely kill myself when I have more time to go? The trick that you have to understand is you are never asking V15 directly. You are computing V15 based on V14, V14 based on V13, etc. Okay, and so you would never have been affected by the terminal nodes in the wrong way because of the way you're doing the max at every point of time. Okay, it's a convoluted answer, but that's really what happens. Basically, you are not ever standing there and saying, I have 15 steps to go, what is my optimal policy? You basically do V15 in terms of V14.
Basically what I mean is like you could potentially sit in a terminal state for like 10 steps.
Yeah?
When, like, so you collect.
But I mean, first of all, the value of the terminal state will always remain.
Okay, so
That's it,
values-
right? So in fact, the value Vk for all the terminal states is always the same.
Okay,
Vk for everybody is the same as their reward state. That was by definition.
okay.
Okay, Vk of all the terminal states is by definition the same as V0 of that state. Every other state changes. Okay? If it's not terminal, then your problem can happen. That means you are repeatedly collecting rewards. But there's nothing wrong with that. In that case. Yes.
I feel like the reward you achieve on the way to the terminal state.
Okay, so the other very important thing to understand in MDPs is there is no goal. There are no goals. In fact, you can do MDPs if these two are not terminal states. You can do finite horizon MDPs even if there are no terminal states. And this exact same calculations will work. In that case, actually, these guys too will change their valuations because they can keep going back to get richer and richer. But nothing in the semantics of MDP stops you, requires you to have terminal nodes. So it's sort of easy to make a connection to A star search and think that somehow MDPs have goals, the goals are the terminal nodes. No. Okay, MDPs generalize the notion of goalness. It's just rewards that you get for being in states. And these rewards are being added up. Sometimes you have terminal nodes, but you don't have to have terminal nodes at all. Okay? So there's a lot more behind those simple equations. And I think you basically missed even I think from what I can see, some of you basically missed even the first order implications. But there's second, third, fourth order implications, that some of which are coming, in the questions that you have been asked. But, so you need to kind of think about what happens to the policies and to the value iteration as we go forward. Okay. So, by the way, before I forget, I was just reminded, there is an attendance. Can I do? I'm sorry. Okay. So, discounted infinite horizon MDPs is what we were talking about last time. All we are doing from discounted, from whatever we did to infinite horizon is what if you are not, there is no actual limit on the number of steps you have to live. Okay, that's a much more general formulation. Okay, and if you have no limit, then it's an infinite horizon MDP. Then most of what you are doing actually works. As I told you earlier, the value backup will still work. Okay, and it's just that at some point of time, the backed up value from Vk and Vk plus 1 will be so close that you'll say, I don't have to back up anymore. And the things that we argued last time, if in fact there were to be a solution for infinite horizon MDPs, it better be the case that the policy, which is the solution, is stationary. Because, again, these are the kinds of things that I can ask and you should be able to answer. What does it mean? Why can't I have a non-stationary policy for infinite horizon MDP? You do realize that we had a non-stationary policy for finite horizon MDP, right? Because it doesn't say, you don't ask the finite horizon MDP, I'm in state S, tell me what the action is. It would say, tell me how many steps you have to live. Then I'll tell you what the